Now, I know you get tired of me yelling at you about free body diagrams, but you know, that's what we get paid to do because it's sometimes very hard to get the right answer without the free body diagram, and nobody wants to pay us to get the wrong answer. So we have to do free body diagrams. So we're drawing a crate here, and I've already drawn this free body diagram, but you know, drawing free body diagrams is fun, so I'm going to draw it again. 392.4 newtons, and then I've got the normal force here, and then I've got the friction force, which will be 0.25 NA, and then I have my tension. And I suppose if you want to do this right, somewhere in here we should draw our sign convention that we normally use when we're doing equilibrium equations. You know, it's good to do that, but then I've kind of established the habit of putting the sign convention directly next to my summation indication so that I don't get confused, because it's pretty easy for me to get confused, so I just do it that way and then I don't have to worry about it. Now, we chose this over this because if we did this first, we couldn't get a direct answer because there are too many unknowns with this one. This one is just fine because there's two unknowns and there's two equations. Using a similar logic, we could sum forces in the x direction, or we could sum forces in the y direction. Both of those are valid. But if I look at this problem, if I sum in the horizontal direction, I have one unknown, two unknowns. If I sum in the vertical, I have one unknown. So if I sum forces in the y direction, then I get immediate gratification, and that's a good thing. So I go minus 392.4 plus NA equals 0. So then my answer becomes 392.4 newtons up as shown. Now, you could argue that this is sort of like spiking a football to say up as shown, but you know, we always want to be clear, and we can see that and we know that arrow is up, but that just reinforces that the arrow is up, and so that's what we want to do. Now, that leaves us with summation of forces in the x direction, which will be like this, and now I'll have tension in the positive direction minus 0.25 times NA back in that direction, and that will be equal to 0. Now I know, at least I hope I do, that normal force is 392.4. Now I'm well aware of the fact that everybody watching this video knew that was 392.4 before I did that, but please don't skip steps, because when you skip steps, that just leads to issues, and I'd rather not have issues. So 392.4 times 0.25, that number becomes 98.1. So then I can say that the tension that's transferred in that direction is 98.1 newtons. And you could also say this direction as shown if you would like to do that. And then what you could then say, sort of as a way of summarizing what we've learned here, is that our friction force at A, which we started out saying was 0.25 times NA, and then of course we said that NA was already 392.4, so we can say that our friction force then is equal to that tension, which is 98.1 newtons. And again, that arrow for the friction is back in that direction exactly as we shown it, and so you just say as shown there. And so what we're going to do is we're going to need that friction force in a moment maybe if we want to, when we get ready to do our summary free body diagram. So we'll just go ahead and write that out. So we take that first free body diagram, we're able to identify all the forces acting on that block, and that's a good thing.